Okay, amazing. Great to see so many of you here today. Thank you for joining. I'm sure a few more people will filter through as we'll get going now. So welcome to this IAQM Early Career Network event, Volcanoes and Long-Range Transboundary Air Pollution. Before I hand over to your host for today, I'm just going to go through some housekeeping things. So to keep this event as interactive as possible, we do set this up as a meeting as opposed to a webinar. But when we've got our presentations, please do mute yourself and turn off your camera to limit distractions. It also means that the recording is a bit cleaner when it comes out and we can put it on YouTube. But then when we go into the question section, please do turn these back on and you'll be able to ask questions by putting these directly in the chat box and they'll be read out on your behalf. Or you can raise your hand and ask questions directly. Just to give you a bit of an idea about the agenda, in a minute I'll hand over to your host. There'll then be 2 expert presentations, followed by 15 minutes for questions, and then we'll have a bit of an update on IAQM activities after that. The event has been organised by the IAQM Early Career Network Subcommittee, and I'm pleased to now hand over to one of the members, which is Emily Portigill, who will be introducing the speakers and chairing the session. Thanks so much everyone for joining. Emily, over to you.
Thanks, Ethne. Hi, everyone, and welcome to our event today. So as Ethne said, we'll be hearing from 2 speakers exploring the topic of transboundary transboundary effects of volcanic eruptions, both using case studies for the example. So one case study is the most recent volcanic eruption that happened in Tonga, and then also the very famous 2010 eruption in Iceland. So our first speaker is Nicola Stebbing, and she will be presenting on how to model the dispersion of pollutants from high altitude eruptions. Nicola is an early career scientist, and she's worked in the Met Office's atmospheric dispersion and air quality team since graduating from the University of Reading in 2019 with a master's in meteorology. Sorry, I can't say that word. And climate. Her research has spanned global impacts of volcanic eruptions to local scale air quality events arising from industrial fires and chemical leaks. And then our second speaker today is Scott Hamilton, and he will present a case study of the air quality impacts of volcanic eruptions. Scott is a chartered scientist with 20 years experience in air pollution dynamics. He is an associate director in Ricardo's Evidence and Policy Business Unit, and his current interests include meteorological and chemical transport modelling, programming and hybridization of machine learning and standards in air quality models. So once we've heard from them, we'll have questions. So yeah, as Ethne said earlier, please either write them in the chat or do raise your hand and you can ask them directly. And then we're moving on to hearing from the Early Careers Subcommittee on wider work in the IAQM and then activities planned further in the year. So Nicola, if you'd like to take it from here.
Yeah, I will set up sharing my screen. And on the right side, you should be seeing the first slide of my presentation.
It's not showing us for us, Nicola. Have you pressed the share your screen button on the Zoom?
I selected the screen, did not click share.
I've done that many times.
There we go.
Thank you.
So yeah, as Emily said, I'm Nicola Stebbing. I'm an early career scientist at the Met Office. And today I'm going to be talking about the recent improvements we've made to the Met Office's modelling capability for high altitude volcanic eruptions and seeing how well they hold up when applied to the real eruption of Tonga earlier this year. So firstly, what do we model and why do we do it? So at the Met Office, we have an operational duty to provide information on the expected location of volcanic ash in the atmosphere to the aviation industry. And we do this as our role as one of the 9 global volcanic ash advisory centres. And together we provide this information because of the hazard that volcanic ash can present to aircrafts and their pilots. So to produce our volcanic ash advisories and graphics, we use our numerical atmospheric dispersion modelling environment, or NAME, to model the dispersion of volcanic ash. Now, as a Lagrangian dispersion model, it models the dispersion and transport of many individual particles using the input weather information from the Met Office's unified model, along with information on the eruption itself based on observation data at the time. Now, while not operational, the same methodology can also be applied for modelling volcanic SO2. And recently there has been ongoing research in the field into whether SO2 could have an impact on aircrafts and their passengers. So it's a good thing we're already looking into it. So what about our modelling capability for high altitude eruptions? Well, until recently, we couldn't actually model above 30 kilometres operationally. This is because of the sort of computational extra power that would be needed to do this. And if you think about it, if there had been an eruption higher than 30 kilometres, say 35 kilometres, whilst we still had this state, you would have had something like the right-hand plot, where I'm comparing in the blue, this is where if you have all of your Met available, you can see where the forecast ash cloud goes. But when you only have part of the Met available up to 30 kilometres, where over it's pink, but overlaid it makes purple, you end up missing this entire section off to the northeast. And that's obviously a problem when we're trying to forecast the areas of risk to the aviation industry. So unfortunately, thanks to computational advancements and improvements to our NAME model, we can now start using Met data or modelling for plumes above 30 kilometres. Now there's a slight hiccup here in that we can't actually, because of how long it takes to set up the extra Met feed with the Met data above 30 kilometres, for the time being we have to use sort of an interim solution, which is what I'll be describing today as a persisted Met approach. So if you now look at the middle plot, this shows an example wind speed versus height plot. And you'll see that from 30 kilometres, the wind speed has been persisted, as in we're assuming that it's the same above this height, and using the assumption that because it's in the stratosphere, hopefully any differences based on the full compared to the full forecast will have a limited impact on our forecasted ash forecasts, versus the wind in the blue line, which is what our full forecast predicts. Now, you might be wondering, well, we've decided to use this, it must be doing a fairly good job for lower down in the atmosphere for the aviation industry. Why are we going ahead with going on involving the extra Met data if it's doing a good job anyway? Well, the problem is, although if you now look at the plot on the right here, which is comparing the full Met approach versus the persisted Met approach, and this is for heights in the atmosphere at flight levels where aircraft fly. Here you'll see there's practically no difference in where the ash is. The entire cloud area is purple. But once we start looking at the total column, which is looking at all of the layers in the atmosphere, which is what you'd be using to compare to observation data, you'll see that using the more resolved full Met forecast, you have this extra feature off to the northeast, which we don't see in the persisted approach. And in other situations, you can also have where the persisted approach, because it's not capturing as much variability in this upper level Met, you don't get as broad a dispersion, which could also form problems when making comparisons. And equally, because it's well known that wind speeds tend to increase in magnitude with height, there can be a difference in the dispersal speed at these heights. So here, the ash cloud from using the full Met approach has travelled further west than the approach using the persisted Met because the winds are faster there. And whilst doing this research, the conclusion was that we still need to go towards this because we would assume that this will have problems when making comparisons to observations such as satellite data, but we don't actually have any events to prove this against. But now that Tonga's occurred, and this is well observed to have emissions above 30 kilometres, we now have an event to compare against. So the eruption of Hunga Tonga, Hunga Ha'apai, apologies if the pronunciation is wrong there, in January of this year, was preceded by some mild eruptive activity from mid-December before concluding in this series of explosive eruptions on the 15th of January. Now, the observations at the time indicate that emissions of SO2 were of the order of about 0.4 teragrams, but the heights of these emissions were getting to in the atmosphere, there was some uncertainty about, depending on how far into the eruption you were looking. So for example, within the first day of the eruption, this is now showing a satellite reading. So this is a satellite profile of aerosols in the atmosphere. And the way this is taken from this ozone mapping and profiler suite is that rather doing a top-down approach, which most people are familiar with satellites, this looks sideways through the atmosphere, which gives us these profiles. And on the 16th, there was indication that the volcanic cloud was reaching heights between 20 and 30 kilometers. But by the next day, when another sounding was done, there was indication that there was aerosols up to 35 kilometers, which is this bit somewhat in the middle and disconnected from the lower clouds. So, and in addition to this, we're also aware that ground observations from Reunion Island, which is to the east of Madagascar, had observations using LiDAR equipment from around the 19th of January. And we'd already done some initial modelling observations using this 20 to 30 kilometre height range for our plume. And when you look at this, and you'll wait for it to restart, by the time it gets to Reunion Island, and actually if you wait until it gets to the 19th there, it's still in the middle of the Indian Ocean, and it doesn't get to Reunion Island until a few days later, around the 24th, which almost seems to indicate that our model cloud is not dispersing fast enough, which adds further weight to the fact that maybe our model plume is not high enough and reaching those higher altitude, faster winds. So using this information for the following comparative plots, I'm going to be using a 20 to 35 kilometer plume height. And we can now start comparing our persisted Met approach to the full Met approach. And hopefully you can see here that both volcanic clouds are spreading out further than the lower plume did originally. But again, once again, the persisted Met cloud is not reaching Reunion Island in the time period we're aware of. But if you watch the full Met approach now that it's restarted, it's spreading much more quickly and further along. And in fact, this period here where it starts to cross over is around the 20th and the 21st of January, which matches our timings for when we know there was observations on Reunion Island. So this is a good indication that 35 kilometers and using our fully resolved Met is a better option. So going on from this, we can now dig a bit deeper and look at some other satellite observations from earlier in the event. So if I start here with a satellite observation from the Tropomi SO2 instrument, you can see that at this point in time, on the 16th of January, according to the observations, the volcanic cloud has spread further to in line with New Zealand and actually is over New Caledonia, this sort of long island, which is just at the edge of where the observations are cutting off. And when you look at the persisted Met approach, our simulated cloud is not reaching that far in this time period, but our full Met approach is. But you might notice in both of them that neither of them have this sort of tail end of SO2 sort of trailing over the start of eruption over Tonga, which you can still see in the observation data. So possibly we're missing something else in our forecast here, rather than just a difference in Met data. So if we move on now to when the volcanic cloud was observed over Australia, we can see once again the full Met cloud has spread much more quickly and is further into Australia than the persisted cloud. But with this, it's actually possibly traveling a bit too far. It's only doing a better job than the persisted Met because the persisted Met is the cloud is only just into Australia, but the full Met is possibly going a bit too far at this point. But if you think about it, if we were just using the persistent MET approach and that was our answer, we would immediately be thinking, well, our MET maybe isn't right. It's not making our cloud travel fast enough. Whereas by using the full MET approach, we can see there is winds available in our data that will get the ash to this location in that time. But maybe we've set something else up wrong in our model setup, in the other variables which have got uncertainties in them, such as the plume height. Maybe our plume is too high, or the release amount of SO2, maybe we've got too much or too little, or even maybe our plume hasn't gone low enough, and maybe that's why we're missing off the tail end of the volcanic plume. And it's the fact that we know better what our MET data is showing, that it's better resolved, means that we can look with more certainty into the other sources of uncertainty to try get a better outcome whilst modeling during an event. So in addition to this, if you remember before when we were looking at the plumes from my earlier research, other things we were missing were distinct features. And at this point in time, when the clouds have reached off the edge of Australia, you'll notice in the observations, and I apologize for the slightly doctored images to try and get Australia to look normal, you'll see that the observed volcanic cloud is somewhat bending back on itself over northwestern Australia. And the persistent plume, the cloud is just going straight off the coast. But in our full MET approach, we do see this slight bend in the ash cloud, or in the SO2 cloud even, which seems to imply that we are using the better MET is having more advantages than just having better timings for arrivals, but equally it's better resolving the variability in the wind speeds and wind directions, helping us better match to satellite observations. So overall, what can we conclude from this? Well, using the persistent MET data can affect both the speed and direction that particulates will travel within the stratosphere in our model, whereas using the full vertical array of MET data can improve our comparisons to observations and give us more certainty into where to look for where there might be problems in our modeling setup. And using the best available MET data, it allows us to better target where to investigate the source of uncertainty. Even if using the better resolved MET data were to imply that our MET was completely wrong, we would have more certainty in that than just thinking, oh, maybe it's because we've persisted the MET data, maybe we're missing something. Whereas at least if we have all of our MET data available, we can know for certain whether it's the MET data or whether it's because we've persisted it. And this kind of conclusion is things we can carry on to other areas of atmospheric dispersal. Using the best MET data will give us better results when dispersing our whatever we have in the atmosphere. So thank you for watching. I hope this has given some insight into the work we do here at the Met Office to help both the aviation industry during volcanic eruptions and also improving the science behind our modelling procedure to best balance the optimal run times along with the underlying science itself. Thank you.
Thank you, Nicola. That was really interesting. If anyone does have any questions, please feel free to put them in the chat and I can read them out after. So now we'll move on to Scott's presentation.
Okay, let me just try to share screens. Tell me when you can see it. Does that come through okay?
Yeah, looks
can see that.
Oh, okay. So thank you very much to IAQM for the opportunity to come and speak to you guys. My presentation is about, I suppose, the air quality practitioner in the UK's view of the Icelandic eruption that happened in 2010. So just to introduce myself, I'm an environmental engineer by training. My PhD is environmental engineering from way back when, and measurement systems actually, but I've since diversified in the air quality modelling, and I've been with the IES and the IAQM for probably longer than I care to remember by this point, probably 12 to 15 years, something like that. And I got my chartered scientist through the IES back in 2010. That was something that I would really recommend. So I've been doing this for quite a long time, but in part of the what that brings is that we have some lived experience of some volcanic activity from 2010, which when I think about it seems like yesterday, but really it was quite a long time ago now. But so my talk is more, what did we see on a practical level in the UK as that eruption was taking place? There was lots of unknowns, and the news stories around that eruption were fairly hysterical at the time for some reasons that we'll talk about. But what did we measure? And at the end of the day is the focus of what I'm going to talk about. So quick primer, what are we talking about? And this informs what we're going to talk about at the other end of my talk when we talk about the species that we were measuring and the UK networks at the time. Primarily, we were interested in particulate material and sulfur dioxide, although the typical emission profile from an eruption is very wide-ranging, and some of the main species are on the slide there. But primarily, we were interested in the particle aspect of the eruption and how that was transferring or transporting to the UK. So just to put volcanoes in some context, these numbers are probably a little bit out of date, but in terms of the production of the international global production of particles from volcanic eruptions, it's quite small in the context of everything else that goes on in the world, particularly around the anthropogenic and the rest of the natural sources that are out there. So it's not the main source of PM by any stretch, I suppose, around the world. And the sulfur dioxide context, again, it's a minor component of the total compared to other aspects. So I just wanted to set that context because I think it's important when we're talking about sort of potentially quite large global scale health effects. The types of hazard, I suppose, and you probably remember back to your studies for a human health hazard to present itself, or a consequence. Let's say we need a source, a pathway, a receptor, and then the consequences, the health effects. So Nicola in her presentation was talking about emission plumes being, or dispersing plumes at some kilometers above ground level. What I'm talking about here is when they ground, and when they ground at locations that have people, and you have a sensitive receptor group, and then you have a health consequence potentially. So the source pathway receptor consequence chain is complete. So again, generally we're talking about aerosols, whether they be primary in origin from the eruption itself or through secondary processes in the atmosphere, through condensation processes, etc. So volcanic PM is a bit of a mixed bag, I suppose, of primary components with the sort of crystal origin, and more particles that are formed through chemical reactions. But I think it's fair to say that the sulfur and the ash are probably the two things that are, or the sulfur dioxide and the ash are probably the two most important from a health perspective. There's an excellent, I'm not going to really go into much depth, obviously time doesn't allow, but an excellent paper, very recent, and it's open source. And I think it does a really nice job of setting out some of the problems that there are in ascribing health impacts to volcanic eruptions and emissions from those. I pulled out some of the main findings. The evidence base is weak on which parts of the volcanic eruption emission might be responsible for negative health outcomes. It's very difficult to conduct health impact assessment studies while an eruption is happening because people that are affected have other concerns to deal with. Exposure assessment is not mature in this context. I'm not aware of methods that air quality practitioners would use to even assign health effects to in the UK quite distant volcanic eruptions. Nicola was talking about some improvements to MET and dispersion models, which excellent. That will go a long way to improving some exposure assessment methods, but the tools are just not in wide use in the air quality modelling community that I sit in. So yeah, there's just a real bag of uncertainty and difficulties in ascribing health effects to any of this, although that paper does a pretty good job of summarising the state of the evidence. The one I'm talking about, the let's call it the Icelandic eruption, quite difficult to pronounce the name. There's some epidemiological studies that were done post-eruption that looked over time windows of up to 3 years or so, but were quite localized, looking at Icelandic populations. There is a study referenced in the paper that looked at the UK, and they found no sort of causal relationship between the eruption and any health effects that were monitored in the UK. So that kind of speaks to the distance proximity type part of the source pathway receptor chain being the further away the better, I suppose. In summary, that paper is excellent and it's open access. The link is on the slide there. So what about the Icelandic case? And for anyone that's interested, the English phonetic pronunciation is on the bottom left there. It's Hea-fia-tla-iakutul. Now, I'm reading that. I haven't memorized it, but I watched that. There's an excellent YouTube video that's about 30 seconds long that you can learn how to say that word. So I was quite proud of myself when I learned it. Anyway, so we were the air quality forecasting sort of agent, I suppose, for the UK government at the time. This is back in 2010. So we had this sort of watch and brief on all sorts of things that were are going on in the air pollution world, let's say, to keep the government up to date, I suppose, is the main thing, so that they can keep the population up to date. So we started seeing some volcanic activity, started off from a nice pristine sort of, I think a glacier caldera, and the thing started waking up in late March, to the point where in mid-April there was a significant explosive eruption. And by the time this was happening, we were already in discussions with DEFRA and partners about, and the Met Office played a crucial role in that as well, when it come to safety information to inform airlines and things. And that's where it all got really controversial, was when planes began to be grounded because of the potential safety effects of this plume. And hopefully my little video will work. I mean, I think sometimes the getting a sense of the scale of the source is, I mean, that just is a gigantic source of emissions, sort of churning away. So it's kind of natural that people might be, and governments and agencies might be concerned about plumes originating from something like this. It's just astronomical in scale compared to some industrial sources, road sources and stuff that we might be more used to. So what did we find? What did we see in the UK through our sort of modelling measurements, and then what did we communicate? So the very early event, and towards the end of the third week in March, the volcano started erupting essentially, and we informed DEFRA about that event immediately, and had the conversations with them, but there was nothing showing up in any of the air quality measurements in the UK at that time. So we concluded that there was no consequence on air quality, and the airspaces in the UK were not affected at that point in time, but that sort of changed over the couple of weeks that followed. As we moved into April, there was the volcano was still erupting, but there was a further explosive eruption in mid-April, and colleagues from the Met Office and the VAC recommended that airspace be closed for, and I think it was closed for 6 days. My memory is a bit sketchy on some of this, it's quite a long time ago, but so we were running the air quality forecast for the UK government at the time. Part of that we run sort of forward trajectory air mass models that tell us where the air masses are originating, or where they're projected to travel to from a location. So around this time from Iceland, all of the air masses from Iceland were heading towards the UK. for a couple of days, which coincided with a very large explosive eruption. So a combination of things, the source pathway receptor chain was sort of, all aligned so that we would potentially see impacts in the UK. And the media started, well, for want of a better term, freaking out. There was almost constant news coverage on this, I think largely because of the implications for flights. Everything was being cancelled. The airlines were very nervous about losing money, and it was very, very disruptive. And it's the only time in living memory for me that I can recall dispersion plumes showing up on the evening news. I don't think it's happened since. I might be wrong, but yeah, it wasn't because of, not as I remember, it wasn't because of human health. It was because of planes being grounded. Really was. So what did we do and what did we see? We were the company that I worked for, Ricardo. We were AEA Technology back at this point, and we were responsible for the management of the AURN, or the QA/QC of the URN and the data management. So we had a very excellent observational live data set that is across the whole country. It's real time. It's covering the pollutants that we might be interested in. So that was nice that we had that already. The modelling I mentioned, we were running high split. Again, colleagues from Met Office and other European partners were running all sorts of models predicting where these plumes were gonna travel. We had a need to understand whether what we were measuring might be because of the volcano or what might be coming from other anthropogenic sources. So we, as the forecasting agency at the time, were running a model called CMAC. So that had all of the anthropogenic emissions in it for the UK, Europe, but we didn't have a source term for the volcano. So we knew that. Sorry, I just got a prompt to say recording had stopped. Hopefully we're still there. So we were running CMAC for everything else, but not for the volcano. So we could see what was coming from local and European sources and what was to ascertain whether the volcano was playing any role, I suppose, in the measurements. And the way that was communicated to the public, update bulletins were prepared almost daily, I think, at one point for the government, and they were published with our air quality forecasts that were published on behalf of DEFRA and the devolved governments daily already. The plume and the eruption, they really were just bubbling away for a couple of weeks. This is the network around the tip. So on the right hand side of that plot, that's a handful of the URN stations measuring PM10 round about the 15th of April is the end of that plot, when we have the models, the Met models are telling us that the air masses are going to be coming into the UK from Iceland. At that time, we weren't seeing anything. There was no PM at least reaching ground level in the AURN network. So as I say, we were modeling where, sort of like in a predictive sense, where the air masses were going to be coming from and when they might enter the country. So this gives us a fairly good indication of when we need to where in the measurement record we might see these potential effects from the volcano. And again, it's worth stressing that we're talking about ground level measurements here. So the plume may be overhead. We're not measuring that. We're measuring ground level where the sensitive receptors are. It was a very busy time for lots of agencies. The Met Office had a crucial role, as I say, and sort of a lot of the evidence behind this event. But agencies in Europe were also interested because they were being affected also. So shout out to all of the other groups that were busily modelling this thing at the time it was happening. As we moved through April, there was still air masses travelling down into the UK from Iceland. Bear in mind, the source is still erupting, still producing a lot of stuff, let's say. We didn't see much of anything actually in the ground level measurements, which, I mean, this was a new thing for us. We'd never really had a case study where a fairly nearby volcano erupted, so everyone was sort of waiting with bated breath, and then nothing really happened. To be honest, we were expecting peaks, and we were expecting the whole network to go up. It really didn't. I suppose is the take-home message. We saw a bit of an increase in Northern Ireland a bit later into the event. This is now almost a month later from the initial episode. There was another eruption in mid-May. Again, we had the models telling us you're going to have a plume arriving in the UK. We still didn't see anything. So what we were basically telling the government and the public at the time was there's no sort of meaningful, tangible effect on UK air quality levels at ground level. What we did think we could spot was I don't know if you can see my cursor, but there's a bit of a peak on around the 4th of May in Northern Irish PM, but it wasn't large enough to really be categorical and say that it was definitely because of the volcano. We didn't see other pollutants going up along the same time, which indicates a sort of some source that is only producing PM and not NOx or SO2, etc. So that's about as much as we observe was like this little small short duration peak in Northern Ireland. So what can we conclude from all of that? And the eruptions petered out sort of the 3rd week in May, roughly. So just to conclude, I mean, I think the literature does suggest that there is a human health burden associated with volcanic eruptions, although it does seem to be very close to the eruptions is where the most of the hazards exist. The exposure assessment tools and methods are just not mature and not widely available. In the UK, there's no reported link essentially between the Icelandic volcano, at least, and harm to health. We just did not see significant ground level impacts, at least at the level where you could be certain that they were coming from the volcano. I think what it does say is that the UK is very well prepared and ready to track things like this. I mean, this is 12 years ago. Probably we're in an even greater state of readiness now that we have PM 2.5 measurement networks, and some of the modelling that Nicola talked about is probably improved in 12 years since this happened. But the UK, I'd say most of Europe is quite well prepared to catch incidents like this. And if I had to come up with a hunch, it's probably that it's not a big deal for health in the UK compared to other known pollution sources, just because of the proximity. I mean, I think it would be a different story if you were nearer to a volcano, perhaps, but in the UK, I think we have other things to worry about, to be honest. So that's me. So thank you for listening. I think we're going to take some questions. Thank you.
Great, thank you very much, Scott. So yeah, now it's time for questions. We have 15 minutes to ask questions, so I'll try and split it half and half, depending on how many questions we get through. We do have one question for Nicola. So the question says, I was just wondering, what are the other sources of uncertainty in the predictions, and what is your theory of the most significant source of uncertainty?
So in terms of during an eruption, a lot of the uncertainty relates to information about the source of the volcano itself. So we can most of the time, so long as the area of the volcano is well observed, we can quite often tell the height quite well, but it's normally the information to do with how much either ash or SO2 has been released by the eruption, and equally sort of the properties of those particles. So depending on the kind of event, you can get lots of fine ash particles or larger particles, and that can affect how our model deals with them. So it's mostly smaller scale things like that which is most uncertain. But equally, depending on how well our MET model was doing at the time, the weather can be a large source of uncertainty. So we do have the option within the office that if we know that the Met Office is not doing a good job that day at forecasting weather, we can use the ECMWF's model. So we do have options there. and we can also vary information based on information we get from volcano observatories. In our case, that would most likely be from Iceland and the Icelandic Met Office. But yeah, a lot of the uncertainty comes down to the actual event itself, as things to do with how much acid has been emitted. It's quite hard to measure when it's coming out, and normally it's measured after an event once it's on the ground, and you can measure like how deep the layer of ash is and things like that. So quite often a lot more information comes out after events, and a lot of it is just so uncertain during it because it's still ongoing. So I hope that answered the question.
Thank you very much. Any other questions? That's the only one we've had submitted so far. Here's another one. So this is for Scott. So how close to an eruption similar in scale to that of 2010 would you expect to see noticeable increase in ground level pollution concentrations?
I think it's it's very difficult to say. I think based on the Icelandic eruption, because in basic terms, I mean, the volcano is largely surrounded by water. You know, there's the epidemiological studies in Iceland did find a causal link between the eruption and health effects. I'm not sure about what they measured on the ground in their measurement networks, but yeah, it would be a more instructive case study had it been on mainland Europe, and you can easily obtain ground level measurements from countries throughout Europe. But yeah, as far as I understand it, there's just a scarcity of measurements. I mean, the plume doesn't seem to ground, generally speaking. I mean, we were tracking concentrations even in like the Shetlands and the Faroes at the time, and they were supposedly right in the plume, and we couldn't measure anything that you couldn't rule out as being instrument noise or potentially like sea spray, other types of PM source. So that, yeah, it's not a great answer. I appreciate, but it just seems like the plumes don't ground very quickly, and by the time probably they are grounding, they're potentially thousands of kilometers away from their source, so quite dispersed at that point. So that the instruments are just not going to pick much up, to be honest. But so yeah, I don't really think that answers your question, but that's the best I can do, I think, right now.
Thank you. We've got another one for you as well. So have you ever seen ground level air quality impacts in the UK for another non-volcanic long range / transboundary event?
Yeah, so we often see very observable peaks from like Saharan dust. Not often, maybe once a year, probably good average. But those most certainly do show up in the monitoring network, and I think largely because they originate at ground level, they don't really have any thermal buoyancy, so they're fairly low height. They travel across large distances in the lower part of the atmosphere, so we can measure them. The other one is we quite often see secondary particulate formation from agricultural practices in northern Italy that translate to secondary PM formation as air masses come west and north. And at the UK, and that can be 30, 40, 50 micrograms of PM 2.5 lasting for a few days. So that definitely does show up in the measurement networks. But so yeah, big natural stuff like deserts, yeah, they do affect us sometimes, but big anthropogenic area source type activities to do with agriculture also affects us quite. And conversely, I mean, I'm sure the European colleagues are picking up UK practices agriculturally and their measurement networks through secondary formation of PM over hundreds and thousands of kilometers. So yeah, we do see it. Yeah, it's just very source dependent, I suppose, is the conclusion.
Great, thank you. What height was the 2010 Icelandic plume? Do you know?
The figures that I've saw in the literature are sort of suggesting something about 8 kilometers. I don't really, I'm not an expert in volcanology. That's just, yeah, me as I understand it from what was reported at the time. From what Nicola was saying, that sounds like it was quite low compared to the Tonga eruption.
Yeah,
I might be wrong about that.
I've heard similar values for the AR eruption, but obviously I wasn't in the office at the time. Yep. Yeah, in terms of like the eruption for Tonga, that's quite high for an eruption, which is why in the past, at least for Iceland, we didn't have the modelling capability above 30 kilometers because we considered that to be quite an unlikely event. There's approximately 4 volcanoes which have historical sort of evidence from ash layers, which scientists have estimated would have produced a plume height of about 30 kilometers, but a lot of them sort of below 20 kilometers and such are more likely, which is why we didn't have that capability in the past.
Thank you for that explanation. Does anybody have any more questions? We've still got time. Oh, just got a couple come through there. So first one, Nicola, have there been any serious consequences of using the less accurate persisted MET approach before having the full MET approach?
So because both approaches are actually quite new, and the last big event that we had in the UK was back in 2010, and this has only been sort of introduced in the past year, so we haven't had a real event to compare it to. But in terms of the sort of research aspect, when I was doing my stuff behind it, in terms of the impact on the effect on the heights at which the planes would be flying, the impact there is minimal. So the forecast there would likely remain the same regardless of which input you used. It would be when you were comparing to the satellite data to sort of validate the location of where you're forecasting your ash cloud to be. That would be where you'd see differences, and that could be where you have problems as to, oh, the satellite's saying it's here, using the persisted approach is saying it's not quite reaching there. That could be because you're using persisted MET rather than having access to the full MET available. But so far we haven't had a real event which the London back have been responding to try that against. So the stuff for Tonga has been us doing it as a research project after the fact. It's not within our area of responsibility. So during the event, we didn't have any operational focus on it.
Great, thank you. Now we've got a question for you both. Well, 2 questions. How long would you expect to see the impact? How long could you expect to see the impacts of volcanic eruptions? I suspect the size of the eruption will have an impact. And then could you model the long-term spread/impact?
So in terms of, for us, the limits to us running a model out for a long period of time is so long as we have the MET data, and then actually if it's running too long, are we going to run out of computational resource to run the model? And obviously the longer period of time you're modeling your forecast for, the longer the run will take to give you output. But in terms of how long you would see impacts, that's not really my area of expertise, but I know that there's quite a lot of stuff to do, like climate aspects of SO2. People often talk about if it gets into the stratosphere, then it can cause climate change or impact climate. But the things we're mostly concentrating on in my area is mostly the short range of things in terms of at the lower heights where planes are. Although from a scientific point of view, it's interesting either way.
Thank you, Nicola. Scott, do you have any input in that? I think you're on mute.
I think that's it.
Yeah.
Yeah, I mean, I suppose the duration of effect. I suppose it doesn't just apply to volcanoes. Any sort of very large pollution source, like I mentioned, dust storms and agricultural emissions and things like that. I mean, in my experience, whenever you're doing anything that's sort of like regional or even continental scale, things clear very quickly, generally, if the source is removed. I mean, it's, I think my experience has always been that you're sort of down, after a few days of, say, an emission event occurring, you're down into background levels within a couple of days of it occurring, notwithstanding any sort of unusual meteorology that might create sort of stagnant conditions over a country or recirculation or whatever. But generally speaking, a couple of days. And I think for volcanoes, so much of the emission is either going to fall out. The particles are on the large side, so they'll fall out of the atmosphere before they ever sort of travel very far, or they're quite chemically active. They'll either be washed out, or they'll form secondary particles, and natural processes will just remove all of that stuff from the atmosphere within a couple of days generally. Now, I think where it's not at all clear is what happens, like Nicola alluded to it there, what happens to species when they are of less interest to health. I tend to work in the sort of health perspective. I don't know if there's any consensus on it's an earth system, isn't it? The complexity involved is huge, and I don't think it's understood at all, really, beyond sort of what's already been described. But a couple of days, long answer to a short question. What was the other part of the question? Sorry, I've forgotten about you asked about duration of effects. There was another part that I don't.
Could you model the long-term spread / impact?
Again, coming at it from a health perspective, the types of like continental, local and regional and continental scale air quality models that we run, we tend to use a lot of the US EPA's regional models. The sources, as I say, you just end up at background conditions very quickly. So yeah, it's sorry, I've lost my train of thought again. But the modeling the long-term effect, I suppose there's a couple of aspects to that. If you mean the long-term effect on health, yeah, there's fairly mature methods for that. Normal air quality modeling methods. Modeling the long-term fate of pollutants themselves, way less straightforward, I think, and beyond using models that can do stuff like deposition and things, removal processes. It's not something that's typically done in my area, at least in the health side of things. Sorry for losing my train of thought there. It's been a long day already.
That's all right, thank you. And this isn't really a question, but from Mark, he said he's recently been to Iceland and went on a glacier hike, and the tour took him under an ice cap where you could see the volcanic ash trapped under the ice, which is quite cool.